Hello and welcome to Week 4, Part B. In this section, we will explain how scatter diagrams and multi-vari charts operate. The scatter diagram is a very useful technique for identifying relationships between two variables without the use of mathematics. It is often the first step in a quality investigation or an investigation as to where a problem might lie in our process. The correlation or a relationship could either be positive, negative, or there may actually be no correlation at all. A positive correlation indicates that variable y increases as x increases. A negative correlation means that variable y decreases as x increases, and no correlation at all means that there is no relationship between x and y. It can also be used to predict the value of variable y based on the value of x. Here are some examples of positive, negative, and no correlation. Here we see an example associated with our pen holder. We see that we've measured the milling or the drill speed. This is our x, and we find that it has an influence on the inner diameter y. We see that there's a positive relationship or a positive correlation as variable x increases. In other words, as the values of x increases, then the values of y increases, and we see a line going upwards. We can also have situations where there is negative correlation. As variable x increases, then variable y will decrease. There may be also situations where there is no correlation at all. The value of variable x has no influence on variable y. Let's take a typical example, and we may want to determine, is there a relationship between the weight and the height of an adult? So we take some measurements. So we take a number of individuals, we measure their height, and we measure their weight. We then plot their height on the x-axis, and we plot their weight in kilograms on the y-axis. And we note that there is a positive correlation. As the height increases, the weight tends to increase. Now, this is the situation in adults, and doctors use this quite effectively, both in adults and in babies and children, to determine whether somebody is at their expected weight for their height. Now, we see that it's not an exact relationship, but nonetheless, we can determine what a typical adult should have, what weight you should have based on their height. And we see an example here. We can fit a best fit line to that, and we see that the best fit line takes into account the best fit to the data that we're presented with. We can then use this to predict what the weight of a particular person with a particular height should be. So we would expect that an individual, on average, an individual that has a height of 185 centimeters would have a weight of around 88 kilograms. So to summarize, a very high correlation or a very strong relationship between the variables is indicated if the dots lie close to a straight line. The closer all the points lie to the straight line, then the stronger the relationship between the variables. If we take, for example, the height, the weight and the height, the data does not fall on a perfect straight line. So while there is a relationship, there's not a phenomenally strong relationship between weights and heights. Just because we have a relationship between the variables does not necessarily imply that one actually causes the other. This is known as causality, and you need to be very careful of this when you're looking at relationships. Let's take an example of the multi-vari chart. The multi-vari chart is extremely useful for identifying the different types of variation that we can observe. There is positional variation, or part or within part variation. There is also part-to-part variation, and there is also variation over time or temporal variation. Here we see some examples. So we've plotted the data on a particular days for Monday, Tuesday, Wednesday, Thursday and Friday. And we see here the variation within the part, we see the variation between the parts, and we see how that changes on a day-to-day basis and over time. We can have specification limits identified at the top, upper spec limit, and a lower spec limit. So in a multi-vari procedure, what we do is we select the characteristic we wish to evaluate. We then take a sample, identify the sample size we're going to take and the frequency of our sampling. We plot the graph with time on the x-axis and a dimension on the y-axis. We connect the observed values with lines. We then analyze and interpret the chart, and we conduct additional studies if necessary in order to make process improvements. Let's suppose that the characteristic of interest is the inner diameter. Here we see we have 3 inner diameters. We have a within piece variation. We also have a piece-to-piece variation. And we also have variation over pieces produced over time, possibly over 3 days or 3 separate shifts. Here we see there are 3 inner diameters on our pen holder, and we see these are actually being measured here. We would like to observe the variation between these inner diameters, both within an individual piece, between pieces, and over time. Now we can observe this on the multi-vari chart that's showing here. The nominal dimension of the inner diameter is 30 millimeters. We see that an upper spec of 33 millimeters and a lower spec of 27 millimeters. And we take 2 items and we plot the inner diameters on the first piece and on the second piece, 2 subsequent pieces produced after each other at 8 o'clock. We then produce other parts are then produced in the meantime. At 8:30 we take 2 further parts. We measure the variation within each part and we compare, and we can then observe the variation within, and we can also observe the variation between. We do the same at 9:30, 9 o'clock, 9:30, 10, 10:30, 11 and so on. Now what we see happening here is that the diameter is tending to increase over time. The within piece variation is not significantly increasing, but we see that the inner diameter of all of them is tending towards the upper spec. This concludes part B of week 4. We will now look at cause and effect diagrams.